Welcome to this video for Senior Physics on Electromagnetism and Electricity. In this video we're going to explore the DC motor and how it works. Now let's have a look at a simplistic diagram of what a DC motor basically is. Now you can see the diagram on the left hand side basically is showing a magnet where we've got north and south, which is denoted by the green bars. We've then got an armature. Now a basic armature is something similar to this model here. Now you can see here basically what we've got is two armatures actually working together. In the diagram here we can remove one of them, and what you're noticing is that you've got wires. Those wires basically are going to be the vertical lines, and they will be in contact. Now what will happen is the current will flow through one side and then come out through the other. Now what tends to happen is that running through the center of the armature there is going to be an axle. So here's the axle that you can see here. Now the axle is basically stationary, and due to the forces which are generated due to interaction between the stationary magnetic field and the magnetic field which is generated in the actual armature, it will spin. Now at the other end what you will find is something called a commutator. Now the commutator, you can see a diagram in the bottom left hand corner. This is the point where the current is actually going to enter into the actual circuit. Now often split rings are used, and these are just copper rings which are attached to the axle, and to those are attached the wires from the solenoid. Now they are linked to the power supply by brushes which are often spring-loaded. Now these spring-loaded brushes basically cause the brushes to make continuous contact, and you can see if you look close up here, you can see that we've got copper and then we get a gap. Then we've got copper and then we get a gap. And then we've got copper and then we get a gap. And the black area is basically the area which is generated due to some carbonization which has happened between the brushes and the actual commutator itself. So basically what does the gap mean? Well, the gap means that we're changing terminals, going from positive to negative, positive to negative, positive to negative, and so forth and so on. Now what we need to do in a DC motor is to get a continuous flow of current flowing through the armature. The thing is though that the armature is continually moving. So as it moves, it's going to change the direction in which the current is flowing. So this side, let's say on this finger, is going to have current flowing in, and this side, my right hand side, your left as you look at it, is going to have current flowing out. Now as it turns, what will happen is they'll swap over. So this side is now going in and this side is now going out. And what happens is we get the same forces which are generated either side of the axle. So I hope that makes sense, and hopefully you'll be able to pick this up. Google commutators and look at some of the YouTube clips that I put on this post, and I'll show you how a DC motor actually works in that relation. So what do we need to know in order to basically work out the concept behind what Faraday said happened with this motor principle? Well, the motor principle basically works on the interaction of two magnetic fields, the magnetic field of the stationary magnet and the magnetic field generated by the current carrying wire. Okay, now if the two planes of the magnetic fields are in the same direction, we are going to get maximum magnetic force. At this point, we basically say that the angle is 90 degrees. However, if the two magnetic fields are at right angles to each other, i.e. that's the magnetic field generated by the wire, and that's the magnetic field generated by the stationary magnet, then we get no interaction at all. And in this case, it's sine theta. Now, if you remember Fibble, sine theta that we dealt with, force equals magnetic field strength times current times length sine theta. Theta for maximum force would be 90, and for no force at all would be 0. Okay, so that basically uses the algorithm and allows us to calculate it, and we will look at that in a different area. But how conceptually does this work? Well, we use the right-hand slat rule, and we work on the principle that our thumb is going to be the direction of our current, Our fingers are going to be the direction of the magnetic field, the stationary magnetic field, and the palm is going to be the force at which it's going to be acting. Now, when we look at an armature like this, remember we've got two solenoids going in different directions. So we basically use the axle to cut the armature in half and say what's happening on either side. Because they're linked, generally what will happen is we will get motion which is going to be circular, and that's how our DC motor works. So let's look at this a scenario, and I'll take you through it bit by bit. Okay, so here's a couple of photos which basically show different rotor coils. Remember, this is similar to what I showed you here, and you can see the commutator there with the brushes, and they would be linking into those copper areas here, which would then be linking to your coils. You've got your stationary magnet or stator magnets, and this is all enclosed in the bottom diagram, which is a typical DC circuit that you would see in any little toy car or what have you. Okay, so how does it work? All right, so let's take the scenario that we've got here. Now, in this case, I've got my split ring on the right-hand side. You can see my commutator. And basically what I've got is the two sides acting. I've got the red dot and I've got the blue dot. Now, they're in contact with each other. So what I'm basically stating is that on the left-hand side of the axle, I've got current flowing out of the armature, and on the right-hand side of the axle, I've got current flowing into the armature. My magnetic field is running from left to right, north to south. So the first thing that I'm going to look at is put in my magnetic field. Now, my magnetic field on the wire coming out can be generated using the right-hand grip rule. So again, use your thumb. From your right hand, it's coming out of the page, which means that my fingers are going to be going in an anti-clockwise direction. For the wire going in, it's the opposite. It's going into the screen, so I'm going in the opposite direction. Now you can see that the wires, the field line directions at the axle point are going in the same direction, but because the axle is solid, there's no forces which are going to be generated. Likewise, on the outside, the left and the right, there is no interaction. Now remember that these are going to be working at 90 degrees to the magnetic field. So let's just put our magnetic field in, and you can see it there with the purple lines. So to the left and the right of the wires, you can see that the magnetic field's going this way, and the magnetic field from the current is going downwards in each case. So they're at 90 degrees to each other. Okay, so what do we do next? Well, the next thing to look at is let's look above and below the wire, because that's where the forces are going to cause the axle to actually start turning or pivot about the axle. Now, those of you who are aware, this turning force is actually called a torque, T-O-R-Q-U-E. And that torque is basically determined, torque can be determined by distance and force. So force and distance from the axle point will give you a greater turning force. Okay, so what have we got? Well, let's look at our left-hand wire. We can see below the wire that the field lines, the red field lines and the purple field lines, are going in the same direction. This means we get constructive positioning happening. We've got the two field lines joining together. So I'm going to get a huge force below the wire. Above the wire on the left-hand side, you can see that the red field lines and the purple field lines are going against each other. This is destructive. This means that the force is going to be smaller above the wire. This means we get an imbalance. I've got a large force below the wire, small force above the wire. The result is the force is going to be moving upwards. So this is a maximum force which is generated pushing up on the armature. So let's look on the other side. In this case, we've got the blue wire, so we're looking at the blue magnetic field lines interacting with the purple ones. Let's look below the wire. Now below the wire, they're going in opposite directions, meaning they're cancelling out. So the field strength is going to be really, really small, so there's going to be a very weak force. Above the wire, we can see that the blue lines are going in the same direction of the magnetic field. As a result, this is constructive. So we've got a large force above the wire, small force below the wire, So the result is that the force is going to be pushing down. As a result, because the current is the same, the magnetic field generated by the red and the blue is going to be identical. The magnetic field of the magnet is also the same, meaning that the force F max in red and F max in blue are going to be the same. The result is I get this turning force. So to recap, at position 1, we've got constructive below the line, destructive above the line, it pushes up. At force 2, we've got constructive above the wire and destructive below the wire, so it pushes down. So what happens, so that the overall effect is that we get a turning force which is generated in a clockwise direction. So what happens then as it's moved through 90 degrees? Well, you can see here that if it moves through 90 degrees, you've got a stationary, our magnet field doesn't change, but you'll see that as it moves from its maximum position up to 90 degrees, and if you look at the commutator, you can see that the wires will not be touching the split ring. If they're not touching the split ring, the result is that there's no current flowing. If there's no current flowing, the result is there's no movement. There's no magnetic field because there's no current, there's no charge which is moving, so there's no interaction between the magnetic fields, nothing happens. However, the armature has got momentum, and this momentum is able to push it past this point where the contacts are not being made, to a point where they will be contact, and then the whole process will occur again. Well, I hope you found that useful, and you can see there that force equals 0 at this position, and as a result there is no movement. I hope you found that useful, and I hope you're able to sort of articulate exactly what's going on. What I suggest you do is watch this a number of times to really clear it in your head. The key thing is to say what's happening to the left of the axle, to the right of the axle, and only deal with tops and bottoms of your armature, because that's where they're going to be interacting. You can then link this with Feeble, F equals BIL, because remember, at the position that you can see on the screen here, theta is going to equal 0. If theta equals 0, the result is that there is no force. As a result, there's no movement. But if it's horizontal, meaning above and below the line, the field lines are in the same direction, theta will equal 90 degrees. Sine 90 equals 1, which means you're going to get maximum force, which is generated. Okay, well, check out some of the exemplary videos which I'm going to be posting soon on how to solve some of these questions, and hopefully you'll find that useful. Thanks for joining me, and I look forward to you watching some more of my videos later on.